Piping vibration, types of excitation and system response, understanding causes and effects of vibrations in piping systems. Overview of tonal and broadband excitation. Excitation in piping systems refers to the energy input that causes vibration. This energy can be introduced in two primary ways: tonal excitation and broadband excitation. Tonal excitation occurs when energy is applied at discrete, specific frequencies, often associated with rotating machinery or pulsating equipment. These frequencies are predictable and can lead to significant vibration issues if they coincide with the system's natural frequencies. Broadband excitation, on the other hand, involves energy distributed across a wide range of frequencies, typically resulting from turbulent flow or complex fluid dynamics within the piping system. Unlike tonal excitation, broadband excitation does not target a single frequency but spreads energy throughout the spectrum, which can still interact with natural frequencies but generally produces lower amplitude responses compared to resonance conditions. Understanding these excitation types is crucial for engineers to predict and mitigate vibration risks effectively. By analyzing the nature of excitation, engineers can design systems that minimize resonance and fatigue failures, ensuring operational safety and reliability. Characteristics and risks of resonance. Resonant tonal excitation occurs when the excitation frequency matches the natural frequency of the piping system. This condition is highly critical because even a small amount of excitation energy can produce substantial vibration amplitudes if the system damping is low. Resonance amplifies the vibrational response, concentrating stress at critical points such as welds and small bore connections. This can lead to rapid fatigue damage and catastrophic failures if not addressed promptly. To avoid resonance, engineers should ensure that excitation frequencies remain outside plus or minus 20% of the system's natural frequencies. This margin helps prevent interaction between excitation and structural response. Resonance is particularly dangerous because it can occur unexpectedly during operational changes, such as variations in flow rate or equipment speed. Preventive measures include conducting modal analysis during design, installing vibration dampers, and implementing operational controls to avoid critical frequency ranges. Understanding resonance and its implications is essential for maintaining the integrity and safety of piping systems. Forced vibration and its impact. Forced vibration occurs when the excitation frequency does not match the natural frequency of the piping system. Although the amplitude of vibration is generally lower than in resonance, forced vibration can still pose significant risks under certain conditions. If the excitation energy is high and the system exhibits low stiffness, the resulting vibration levels can become problematic. Forced vibration typically originates from machinery such as pumps and compressors, where operating speeds generate periodic forces. These forces, even when off resonance, can induce cyclic stresses that contribute to fatigue over time. Unlike resonance, forced vibration does not rely on frequency coincidence, making it less severe but still important to monitor. Engineers should evaluate the energy levels and structural characteristics to determine the potential impact of forced vibration. Mitigation strategies include improving system stiffness, adding supports, and isolating vibration sources. By addressing forced vibration early, operators can prevent long-term damage and maintain system reliability. Nature and effects of broadband energy. Broadband excitation introduces energy across a wide frequency range, commonly resulting from turbulent flow, cavitation, or complex fluid interactions within the piping system. Unlike tonal excitation, which targets specific frequencies, broadband excitation spreads energy throughout the spectrum, increasing the likelihood that some energy will coincide with the system's natural frequencies. However, because the energy is distributed rather than concentrated, the resulting vibration levels are generally lower than those observed in resonance conditions. Despite this, broadband excitation can still lead to fatigue failures, particularly in components sensitive to high cycle loading, such as small bore connections and welded joints. Engineers should consider broadband excitation during design and operational assessments, as its unpredictable nature makes it challenging to control. Preventive measures include optimizing flow paths to reduce turbulence, installing vibration monitoring systems, and reinforcing critical components. Understanding broadband excitation is essential for comprehensive vibration management in complex piping networks. Consequences of vibration-induced fatigue. Vibration in piping systems, whether caused by tonal or broadband excitation, can lead to severe structural issues. High cycle fatigue is one of the most common consequences, occurring when components experience repeated stress cycles over time. Critical areas such as welds, small bore connections, and supports are particularly vulnerable. If left unchecked, fatigue can progress to cracks, leaks, and even catastrophic ruptures, posing safety hazards and environmental risks. In extreme cases, vibration can cause failure of main line welds, resulting in significant downtime and costly repairs. The financial impact includes not only repair costs but also production losses and potential regulatory penalties. To mitigate these risks, engineers must implement proactive vibration management strategies, including design optimization, regular inspections, and real-time monitoring. By understanding the mechanisms of vibration and their effects, operators can enhance system reliability and prevent failures before they occur. Preventive measures and strategies for vibration control. Preventing vibration-related failures requires a combination of design, operational, and maintenance strategies. During the design phase, engineers should conduct modal analysis to identify natural frequencies and ensure that excitation sources do not coincide with these frequencies. Structural modifications, such as adding supports or increasing stiffness, can help reduce susceptibility to vibration. Operational controls, including adjusting flow rates and equipment speeds, are effective in avoiding resonance conditions. Installing damping devices and isolation mounts can further minimize vibration transmission. Regular monitoring using vibration sensors provides early warning of potential issues. Allowing timely corrective actions. Maintenance practices should include inspection of welds, supports, and small bore connections for signs of fatigue or fretting. By integrating these measures into a comprehensive vibration management program, operators can significantly reduce the risk of failures, enhance safety, and optimize system performance.